title of the first talk is Lessons in Practical Machine Intelligence, and it gives me great pleasure to introduce our opening speaker, Dr. Greg Corrado from Google Research, who will introduce us to artificial intelligence, machine learning, and artificial neural networks. Dr. Corrado.
Thank you. Good morning, everyone. It's an honor and a pleasure to be here as your first speaker. And so what we're going to talk about in the first little bit here is actually not so much about how the mechanisms of neuroscience, but how artificial intelligence and machine learning in computer science is being revolutionized by moving ever so slightly towards our understanding of the brain. So I work at a project that's called the Google Brain Project, and it is only very loosely related to the brain, as you will soon see. So this project was started several years ago just as an experimental attempt within Google Research to try to train artificial neural networks at a very large scale. But it's grown and has really taken off and changed the way that we do machine learning at Google. So there are three main objectives of the project that we have. One is we try to build software that allows both ourselves and for outside scientists to do deep learning, which I'll explain in a moment, to do deep learning research ourselves, and also to put deep learning in real products and get it to consumers as soon as possible. But I want to underscore right at the beginning, since I'm at the Brain Forum, that this is not a neural simulation project. So this is not a project that is designed to recreate in detail the functioning of the nervous system, but it's instead an effort to try to build artificial intelligence and machine learning using only a few inspirational pieces of what we know about the brain. So the kinds of things that we do have already led to great progress, both in externally available software. So we've released something called Tensorflow, which is an open source package for using machine learning. We've published a lot of research. I'll tell you a little bit about that. And we also have deployed these things in real products so that this kind of intelligence is in every person's pocket already. So let me explain what is deep learning. So deep learning is a powerful class of machine learning model. But it's a modern reincarnation of something called artificial neural networks, which was originally thought of actually as far back as the 1930s, the idea of trying to recapitulate neural computation in artificial devices. And much of the key ideas were available in the 1980s and 1990s, but it's actually only recently that this has taken off and really changed the face of modern machine learning and computing. It's a collection of simple trainable mathematical functions that are compatible with many variants of machine learning as we know it, both learning from experience and learning from outcomes and simply learning by observing the world. But the point that I want to make here is that this is only very loosely based on some of what we know about the biological brain. So this figure here is actually taken from a neuroscience publication and is meant to be a schematic diagram of how we think object recognition might happen in the primate brain, with successive levels of processing, discovering new and more abstract features about the visual input. But it's also a schematic for how in practice, machines do this very same task. So what are the commonalities between real neural networks and these artificial systems that have become immensely popular in artificial intelligence these days? There are really three simple things. So one is that each neuron is connected only to a small subset of other neurons, both in the brain and in these artificial systems. Connectivity is generally very local. And based on what it sees, that neuron tries to render a decision about what downstream communications it wants to make. So it's relatively a local process, and each individual computational element is not very powerful. But they learn to cooperate to accomplish great tasks like write poetry or build bridges. And it's only through the concerted actions of billions of neurons, whether they be real or artificial, that we get properties that appear to be intelligent. In deep learning, rather than having individual cells that do computation, we have individual mathematical functions. These are really kind of the simplest sorts of mathematical functions that one could use for this kind of task. And indeed, I promise this is the only math you'll see. This is the kind of function that any first-year engineering student would recognize. But the magic is having millions or billions of these working in concert. Each of these individual neurons, they implement slightly different functions, but what function they implement is learned by experience. And the algorithm through which these systems learn is an algorithm that's called backpropagation, and that algorithm has actually, as I said, been known since the 1980s. So it's not a new discovery. But when I was in grad school, artificial vision systems had no hope of recognizing whether a photograph contained a cat or a dog. They could do a cat versus a fire hydrant, but there was no hope of cat versus dog. And now this is something that any first-year graduate student in artificial intelligence can implement. And the way that this is done now is by having these artificial neurons look at local images of the local patches of images, and make decisions that are then cascaded up to progressively more abstract representations. And this, we think, is basically how the visual system works in the brain. And this is something that has led to really surprising innovations in artificial intelligence. These are examples of images that were where a computer actually synthesized an entire sentence to describe the contents of the image. You can see that sometimes it does very well, like describing that photograph as a close-up of a child holding a stuffed animal, and sometimes it fails in comedic fashion, as you see in the lower right there, where it thinks that kite is a man flying through the air while riding a snowboard, which is a very cute mistake to make. You can see why it made it, but it's obviously not correct. Something that's actually been very surprising to us, though, is that these very same techniques have given rise to something that's been very surprising to me, is the ability to use them to actually create art. In some sense, what we're able to do is make these artificial neural networks hallucinate visual imagery. And these hallucinations are often pictorially beautiful and can be exported from the artificial intelligence to make art. And actually, just last year in San Francisco, I think, was the first ever computer-generated art auction. Another thing that you may have heard about is that very recently the game of Go was beaten by Google DeepMind, where the world champion of Go was bested in several matches. And this is, again, about seeing. It's about intuiting. The old rule-based artificial intelligence that allowed us to conquer games like chess simply do not scale to games like Go that are really about pattern recognition. So this is a surprisingly general technology, and Google researchers have published the applications of artificial neural networks in a wide range of areas based on object recognition, speech recognition, machine translation, really almost anything that you can think of. So that's sort of the research that we're doing, but I also want to talk to you just very briefly about how we are both making these technologies available externally and how we put them in real products. So Tensorflow is the open source package of machine learning tools that we use to build our own artificial neural networks, but it's also something that we've distributed widely. We first released this in November in 2015, and it's already the most popular open source machine learning platform on GitHub. And we're hoping that we'll be able to create a machine learning standard that people will use across industry for this kind of technology. The Tensorflow website is both an opportunity for developers and researchers to learn about this particular software, but also to learn the basics of machine learning and sort of get started on this. I believe that machine learning is going to play the same kind of role that network connectivity played in the last decade, where every developer in technology, regardless of whether it's for software or hardware, needs to understand the way that machine learning is going to impact their product. Let me tell you, though, a little bit about the way that we put this into our products. So deep learning adoption within Google has been sort of dramatic in how rapidly it's progressed just in the last 4 years. And we do this both to improve pre-existing products, so for example, last year we announced that even Google search ranking now benefits from an artificial neural network that learns to understand the intent of queries, but also to build products that would have otherwise been impossible. For example, something else that we released last year is Smart Reply, which is an automatic function on your mobile device to synthesize short emails for you so that you don't have to type them for yourself. So how do these kinds of systems work? There's actually a relatively simple pattern, which is that we try to learn from examples. So for example, Gmail spam classification used to work on a set of rules that tried to identify whether a message contained the features that might or might not indicate that it was spam. But now we learn from historical examples and have reached record levels of accuracy. We also use it in speech recognition. So if you have an Android phone and you speak to it, it goes through an artificial neural network system that processes the sound waves in order to try to decode it into text. And this was really a revolution in how well speech-to-text decoding could be done. Likewise, Google Photos uses these kinds of artificial neural systems to recognize objects and images. And actually now you can search your personal photo library for any concept at all without having to have tagged it manually yourself. So you can search for Siamese cats or hugs or whatever the concept is and find all of your photos that contain those concepts because the machines are now able to recognize them directly in the pixels. And this was it's surprising how well this works. So the use case on the left was sort of what we imagined, where someone might be able to search for a statue and get all of their photos of statues. But I really didn't expect that you would be able to, for example, search for Yoda and discover that this doll is the closest thing to the Yoda character in someone's photo repository. Translation is something that we really care about. And again, we think that people learn to translate and speak languages mostly by example, and we think that machines can learn to do that as well. And we think that this is a new growth area for this technology. But one of the things that's exciting is that we can combine these technologies in surprising ways. So for example, a small number of Google researchers worked together to put together a system that was able to use a phone both to recognize the text in an image, automatically translate it into your language of choice, and then project it back in the image. So you have a virtual window onto the world that puts everything in the language that you understand. Smart Reply I already mentioned. One of the things that was funny here was that as recently as 2009, this was something that was a joke even to us. Google announced that Gmail would start replying to your emails for you in 2009, just as a joke. We were kidding. And then 6 years later, it was completely real and launched. And now over 10% of replies on mobile inbox are generated by people accepting the machine's suggestions. The way the Smart Reply system works is that there's basically one neural system that tries to decide whether or not an email might deserve a short response. And then if it seems that it does, there's a second neural system that tries to compose a short response. And this is an example of my brother inviting me to a family event and asking me to RSVP, and the automatically generated responses are, count us in, we'll be there, or sorry, we won't be able to make it. So with one tap, I could have replied to him, but I didn't, and I was in trouble. But I could have. So these are the three kinds of areas that we've worked on. We think that this kind of technology is really changing the face of computing and technology. It is only very lightly related to the functioning of the nervous system, but it's been surprising to see where this revolution is coming from. So just the conclusions that I want to leave you with is that machine learning is already in many of the real products that you use today, particularly on your mobile devices. The data availability, the underlying mathematics and modeling, and computational power are all very important to this. None of these, it's completely impossible to do this with any of these three pieces missing. Deep learning is the current growth area in machine learning and artificial intelligence, but it only has a small number of points of biological inspiration. It is not a simulation of the brain by any means. It isn't magic. It's just another tool in the engineer's toolbox. But we think that this is a tool that's having increasing utility. Google is hoping to establish a standard around TensorFlow as a machine learning tool of choice, and that's part of the reason why we open sourced it, so that we can use the same software as you all do. Okay, and that's it. Thank you.
Thank you very much. I think you're joining the discussion in a moment's time, aren't you? Do you want to find a seat?
Sure, thank you.
Dr. Corrado, that was fascinating. The maths at the beginning slightly threw me, but then I was back with you. What a fascinating start to the forum. I would now like to introduce Professor Aude Billard, who heads the Learning Algorithms Systems Laboratory at the School of Engineering at EPFL, who's going to lead the discussions. Thank you very much. Aude.
Want me to stay here?
Whatever you'd like.
Sit there? Okay. All right, so as I walk, I think I'll get started. Thank you so much, Greg, for this kickoff. Right, so machine learning is certainly moving on to this new field. I like to summarize it maybe with 3 adjectives. I think people are amazed by the results, and you've given us a very good overview. I think they're puzzled by how we achieve that, and we have the issue of, how do you grow the network, how do you choose the structure. These were issues that we already had in the 80s and 90s. And I think they're amused. They're amused by the fact that we are revisiting artificial neural networks. So do you want to give us a little bit of a brief of what has changed in the way that we train the networks now?
Yeah. So this has actually been very interesting. There have been some very important developments in the underlying algorithms for how these networks are trained, but most of the gains are actually through the availability of new computing resources. So the ideas that we had in the 80s and 90s were actually correct. They were great ideas. They were just before their time. And it's been the availability of computational resources, both in the form of GPUs, graphics processing units, that really kicked it off in the academic community. Google announced just last week that we actually have our own custom hardware TPUs that we use to accelerate this even further.
Okay. So as a follow-up to that, machine learning is very data-driven. So the data matters. Google has tons of them. It's a curse potentially, because you may not have a very balanced data set. Typically, you're talking about speech recognition or recognizing text-to-speech. You may have a lot of speech from one type of language and not so much from the others. So how do you deal with that? With the paucity of data, with the different type of data, so that you can have enough to make a very good inference?
Yeah.
You get rid of some data?
So the data are absolutely critical, and one of the greatest opportunities for open research and development in machine learning is changing the way that data are used. So right now, these artificial systems use an enormous amount of data to learn very little. They take thousands of images or even millions of images to learn these basic concepts that humans learn from a very small number of examples. So developing techniques that allow machines to learn from fewer examples the way that people do, I think will be one of the biggest advancements in the next decade.
Yeah, but how do you approach that with deep learning? So typically you have the problem of the curse of dimensionality, which now is brought up by the fact that you have tons of neurons, and then you're quadratic in the number of parameters. So how do you make sure that that you can still deal with this enormous amount of parameters? And
so I think that's been part of the essential tension that's gone back and forth, is that as you make the artificial neural network larger, it becomes more powerful computationally. It can learn bigger abstractions, but its need for data grows even more to train it adequately. And thereby, its need for computational speed grows in order to be able to process that amount of data. So it's this weird chicken and egg where you actually need all 3 of these ingredients in order to move things forward. So the approach has been to try to expand data sets, expand computational power, and then innovate and expand the neural networks proportionate to that.
Okay. Do you want to share a little bit with us the trick of the trade? So how do you build a network?
If I knew what the tricks, if we could articulate what the tricks were, that would be wonderful. But unfortunately, it's actually still the case that this is very much, it's as much an art as it is a science. So the people who are best at crafting these artificial systems are people that have had experience in building them before, and they have an intuitive sense about when a machine is failing to learn, why it's failing to learn. They really don't just teach themselves. And so that's, I think, part of why we want to get the tools out there so that more and more people can have exposure to attempting to build these things.
Okay. Well, I'm happy to continue with the discussion, but I don't know if we want to start opening that to the rest of the floor. What I suggest is maybe some people come up already if you have questions, so that you line up, and then I'll continue asking some questions to Greg as we go. So I'm still curious about the actual structure of the network.
Yeah.
Do you reuse some of this structure? Because you talk about similarity to the brain, so some structures are reused for different tasks. Is this the same? So for instance, do you go from text-to-speech to actually natural language processing with similar type of structure, or are these two different networks?
Yeah, so this is a great question. So there has not been one canonical structure to the artificial neural networks that's useful everywhere, but there are some primitives that get reused over and over and over again. So whenever there's any kind of local structure to the data, the way there is in an image, convolutional networks, which have been around for a long time, seem to do very, very well. Whenever there's temporal extent in the data, recurrent neural networks, which come in many flavors, seem to do very well. But there's still a great deal of experimentation and research to be done about exactly which kinds of structures work best for which problems. It's not the case that there's just a black box that you can present your problem to and it learns to do it well.
Yeah. Okay, I can see that we have one.
Yeah, Andrea Pfeiffer, ACIMMUN, thank you very much for an outstanding presentation. I have a more practical question for you, and you will see I will follow up in the session afterwards. So how can we use this wonderful science to address one critical aspect, which is probably the basis for everything we are dealing with right now in developing medicine, innovative medicine for neurodegenerative diseases, and this is early diagnostic. So how could we in the medical field work with you in the IT field to really add early a word for diagnostic?
Yeah, so I think that medical diagnostics is a great example where the community of people that currently have the available data really should be looking at these new machine learning technologies as an opportunity to change the way in which we do diagnostics. And I think that that's part of why it's really great to get these technologies out there and make them available to more people.
Hello, Brian Rudkin, Stem Cell and Brain Research Institute, Lyon, INSERM. I'm going to perhaps throw you a curveball. That's a lot of data. How much? And in terms of accessing it, there must be a lot of electricity used at some point. If you want to talk about sustainability of all of this, I'm sure you must have some thoughts in that regard, and I'd like you to be able to share that with us.
Sure. So in terms of data, one of the things that's interesting is that the amount of data that's necessary to solve the problem varies based on the problem itself. So in the case of object recognition, the academic data sets that were developed a couple decades ago are actually large enough to develop superhuman object recognition. They're sufficiently large, but we didn't know how to use those data, even though they're available to the entire academic community, until very recently. But it depends on the difficulty of the problem. More data is never worse, but there are definitely diminishing returns, where at some point you don't need more data to build a better email responder or something like that.
But then the question is, how much electricity do you actually need to maintain all of this and to access it?
So one of the things that I think is most remarkable about the biological brain is how enormously energy efficient it is, right? We have in each of our heads something that is far more powerful than any of these engineered systems, and is enormously more energy efficient. And I think that we're in that funny stage where we're just barely getting started and it's ridiculously inefficient and it takes an entire room full of computers and all of that. And that has to change, right? These things have to get smaller, they have to get more efficient. And I think there are huge opportunities for development there.
Igor Kravchuk, electrical engineering student, actually. Touching on that, what do you think is the role of neuromorphic devices and non-von Neumann architectures in processing this data?
Yeah, so that's a great question. So I worked a little bit on neuromorphic architectures in the past. Part of the problem that we're having is that the algorithms, the learning algorithms that we use, are all really based on calculus. And for that kind of floating point precision mathematics, the von Neumann architecture works generally well. The more neuromorphic approach, where we try to recapitulate more of the functioning of the neural circuit in silicon, I don't think we know exactly how to do it. I think that once we figure out how to do it, that will probably be the route to low power computing, but we just don't know quite how to make those machines learn yet.
I'm afraid I'm going to have to jump in. Professor Billard, do you have anything else you'd like to conclude with?
Oh, sure. I mean, I will have plenty of questions, but I'll take that over the break.
OK, well, one of my jobs is to keep us all to time. So I'm afraid we are going to come to an end with this session. But I just want to ask you one final question of what eventually do you think, Greg, machines are going to be capable of doing?
Oh, that's a great question. So, I mean, I think that the capabilities of humans and machines are complementary and have been complementary for hundreds of years, right? And I think it's actually about a process of mutual discovery where we see, well, okay, we don't really want to use shovels anymore, right? We want to use backhoes, right? Or whatever the analogy is. And I think that same kind of thing will happen where we'll see where these intelligences get purchase and where they don't.
OK. We'll leave it there. Ladies and gentlemen, round of applause, please. Dr. Corrado and Professor Billard. Thank you.
Thank you.